I start, let me go one step back and first share a little bit about Airbus as a company, what we are doing. And this picture here captures a lot about us. So you probably know us best for our commercial aircraft. You see two of our products here on this picture. The smaller one in the middle, this is one aircraft from our A320 family. This is our working horse. We have delivered this more than 10,000 times. And every about 2 seconds, one of these aircraft is taking off somewhere in the world. But Airbus is more than that. We are also offering military products. You see here some of our military aircraft on the left side. We have a dedicated division for helicopters. Some of the products are shown here. And what you cannot see in this picture is our space segment. So we are Europe's largest satellite provider. We are producing communication satellites, Earth observation satellites. We are also involved into scientific missions, deep space probes. So our portfolio really covers the full range of aerospace products and also the related services. And we are naturally exposed to a number of challenges. And one of the key challenges at the moment in aerospace is sustainability. So how can we come to sustainable aviation? And Airbus is really devoted to this topic. We are following this in different paths. One is sustainable aviation fuel, called SAF. This is a fuel produced out of feedstock. And naturally, it has a lower or better CO2 footprint than traditional kerosene, and we are making our aircrafts ready for using 100% SAF by the end of this decade. Another very important path we are following is a new development of a zero-emission aircraft powered by hydrogen. It's called ZERO-E, stands for zero emission. And this is actually a very innovative project, not only in terms of propulsion system, but also you see we're investigating here very new types of designs. And it's also quite challenging to integrate this kind of aircraft in the existing infrastructure for aviation. So you see aerospace really requires innovation. This is really important. We are working on a variety of technology bricks, and quantum is one of those bricks, which is becoming more and more important. And so we are steering this topic centrally, and it's very important to know that we are really working on all the different quantum pillars, not only quantum computing. Quantum sensing is important for us, for example, in terms of improving our navigation capabilities. It's really key in aerospace, but there are many applications in quantum sensing. For example, we are currently developing for the European Commission a quantum sensor based on cold atom interferometry, which will measure from space the gravity field of the Earth with an unprecedented accuracy, and hopefully we have a chance to fly this by the end of the decade. In quantum communication, we are one of the key players in Europe in the European QCI context. This European QCI stands for European Communication Infrastructure, Quantum Communication Infrastructure. And we are active here in the field of the network, but also in the field of the space segment development. So today I will focus on quantum computing. Compared to sensing and communication, this is still a little bit ahead. But nevertheless, we are exploring this intensively because we believe it can have a disruptive impact on aerospace and will be very important for us. So why is that? So in Airbus, and I think I can speak for the whole aerospace industry here, we have high computational needs. These can be traditional aerospace tasks like structural modeling, vibrational modeling, CFD, but also big data, machine learning is coming more and more into the game, and requires also a lot of computational costs. So we are operating at Airbus our own HPC centers. They are actually quite powerful to meet those demands. But we already know today that those demands they will increase in the future. So we are looking in our R&D activities to extend our HPC toolsets. And quantum computing is one of the paths which we believe is very promising in this context in the future. So we are coming, as I guess most of the larger industries, from the application side. So we are in the stack coming from an application, then going into the algorithms, also a bit lower in the stack, to understand how quantum computing can help us. We are widely indifferent to the concrete hardware platform. So the KPI, which we have for us, is to have a demonstrated performance advantage for a relevant application. And there are actually many, many applications in the aerospace domain. We are structuring them into 4 what we call use case families. Those use case families, they share a similar way of mathematical modeling. And the use cases are coming from our business unit and are then included into those families. The first one is quantum chemistry, microscopic modeling. Here, fuel cells is a very important topic, but also material properties, similar to what Jay was mentioning in his talk. We have one cluster about optimization, typically combinatorial optimization problems. One cluster about machine learning, where we are challenging classical machine learning techniques with quantum machine learning. And the last one, which is actually quite important for us, which we call quantum solvers, which includes everything around equation solvers with a focus on nonlinear PDEs, partial differential equations. And here applications are, for example, CFD simulations, so aeroacoustics, so very disruptive, very important ingredients for our business. So we have worked about since 2016 at different use cases here, and I would like to use the opportunity today to guide you a little bit through our more recent projects, which we have been able to launch. And the first one is from the chemistry side about fuel cell modeling. So this is quite important for us because I was already mentioning we are developing this hydrogen-powered aircraft, and one of the engine options is going to be based on fuel cells. So Airbus is taking this very seriously. We have found a company called Aerospace in a joint venture with a fuel cell specialist, Elrin Klinger. And we will integrate, and they will produce the fuel cell stack. This will come into the fuel cell engine model. You see here a sketch of that. And on our development roadmap, this is going to be tested at our A380 flight test platform. So you see it's going to be attached here at the rear part and then supplied from the inner part of the aircraft with liquid hydrogen. So why do we need a quantum computer here? So actually, we have specific requirements, in particular in terms of the power density of the fuel cell, but also in terms of the lifetime prediction and lifetime in general. And those parameters are strongly governed by microscopic processes in the fuel cell. So we're focusing here on the first step on catalytic surface reactions, namely the so-called oxygen reduction reaction. That's one of the key reactions at the cathode of a fuel cell, which is strongly impacting the performance. And this is a strongly correlated system. Which means that classical methods like DFT, they have limitations, and we are currently exploring to use quantum algorithms to go one step further. And we are very happy here to work with Continuum and also BMW together. And BMW is giving a talk about this topic in the status here also at this conference, a deep dive, which you're of course invited to join. So here you see an example how quantum computing can help us on the hardware side potentially. To meet sustainability or sustainability goals. But we can also think of using this to operate our aircraft in a more efficient way. And here we have one use case in the area of flight path optimization. We are doing this here with A-Cubed, Airbus A-Cubed. This is our Silicon Valley Innovation Center, very close actually to this beautiful place. So we're exploiting here the ecosystem within this innovative ecosystem. And for us, it's our fast-paced machine to explore, develop, and to deliver fast-paced solutions for aerospace challenges at the intersection of software and hardware. And the idea is here to develop software accelerators to define smart architectures of overall software problems, and then to apply quantum algorithms, quantum-inspired algorithm, and quantum emulation techniques to specific subroutines. We are very happy to work here together with Cuberate, and with them we are exploring a use case to find the most fuel-efficient trajectory between a source and a destination. You see here a sketch, you see here the source, the destination, then this is the flight path. You see a graph around, and each point, and each edge and each node, we can calculate a cost function, and the cost function depends on the explicit weather conditions like wind, humidity, but also the aircraft type, the engine type, and the weight, and of course this is also changing over time. So here you see, let's say, a high-level breakdown of the software architecture, and in specific spots we are now exploring if a quantum-inspired or quantum-emulated technique can help us to speed up the overall software velocity, software performance. So you see this is very specific optimization problems, but we have a lot of those combinatorial optimization problems in aerospace, and so we have started a collaboration with IonQ to develop a quantum-powered tool for those combinatorial optimization problems. We have here a variety of optimization type problems, which are very important for us. And the idea is here to use gate-based computing combined with machine learning enhancement, and we are focusing in particular to have a very efficient constraint encoding. So the idea is that we will develop here a quantum algorithm and exploit this on quantum hardware based on ion computers. So we will hopefully use IonQ's Forte in the next year to implement this software. And here we can really, let's say, avoid a lot of error correction and really focus on the algorithm side. So one of the first use cases we have been looking at is the use case of aircraft loading. So this is something we have already tackled in our quantum computing challenge in 2019. And the question here is, how can you load containers of different size, different weight, different priorities into different slots of one or several aircrafts, and then at the same time meet the center of gravity as good as you can and to remain in the shear force limit, etc. And you see, we can already conduct this in a kind of toy problem set. So here we can load 4 containers into 3 slots, and we can achieve already, let's say, a rather high probability of the best state. So as you know, we are a European-based company, but we are acting globally in quantum. But we are also very active in the European quantum ecosystem. I'm happy to announce that we are now also part of a new project funded by the European Union. It's part of the Horizon Europe program. It's called Equality. Equality stands for Efficient Quantum Algorithms for Industry. We had just recently the kickoff. This project will run over the next 3 years. And here we are developing algorithms for industry-specific workflows and develop also strategy for optimum hardware exploitation in the NISQ era. So you see what we're doing, we're really going through the full stack. We have here a set of use cases coming both from the aerospace sector and the energy sector. We are developing algorithm primitives, and then we have one work package on the hardware-efficient implementation, and we will exploit the European quantum hardware available in the next years for those use cases. So we are very happy to work here in a nice collaboration together with Capgemini, Pascal, Da Vinci Labs, and we have also several academic partners on board, INRIA, Fraunhofer, DLR, and the University of Leiden. So Airbus is leading here the proof of concept implementation for the aerospace use cases. And you see here some of the use cases we are tackling. We are focusing a lot on CFD case, on the airfoil dynamics simulation, and we are trying to exploit here how we can go to higher dimensions, how we can efficiently encode boundary conditions and nonlinearities. So this brings me to the end of my talk. So I hope I could show you that we are taking this topic of quantum computing really seriously. We are exploring a variety of use cases. We're excited about this very fast development in the ecosystem. We are happy to shape together with you and all the other guys in this business this story together. So thank you very much. And I'm here the full conference. So if you have any questions and we don't have enough time, so please feel free to approach me at any time. Thank you.
Yeah, thanks, Doc. Nice talk. Just a quick question related to your flight optimization example that you showed. Maybe it's getting a little bit into the weeds of the problems. Do you have an estimation of the number of nodes of this particular example you showed? Essentially, it's like a traveling salesman problem. So
exactly. I mean,
I'm just wondering.
Yeah, that's a very good question. Actually, this is so if you go back. So the point is, the more nodes you add, you can imagine, the better the performance of this trajectory is going to be. But the solution space is also increasing significantly. So right now, we are working here with toy problems. So this is not yet on a realistic scale, but this is also not yet, let's say, the target. The target is here to really look. Can we find, even if it's only a small acceleration, can we find an acceleration on the toy problem? So we are not yet in a stage that we can say we can go towards an operational implementation. But I mean, we hope very much that the path is then not too long. But I mean, anyway, we have not yet demonstrated the quantum advantage yet.
All right, copy that. Thank you.
Thanks. I wonder, do you expect, are you like in the Boeing camp, where it's a matter of when, not if? And do you expect to benefit with NISC computers, or are you going to have to wait for something fault tolerant and much bigger?
That's a very good question. So I think we are still, I mean, we are in an exploration phase, and this is exactly what we're doing in the moment. So we are following some projects focusing on fault tolerant algorithms, where we are quite sure we find applications where it's highly impactful, but then of course we rely on the hardware development. We have a few projects also in the, focusing on the NISC era, and we were also this project on the flight optimization. This is even, let's say, one step before, where we really try on what is possible right now. And this is already advantages. So we are trying really to cover everything. But I mean, in the end, also from our side, we believe the very big impact, so let's say CFD simulation, this will probably require fault-tolerant hardware.